So to continue on developing models for how the proton and neutron fit together into nuclei of various kinds, and how those models inform what we've seen in the semi-empirical gas model, we want to develop a model called the Fermi Gas Model. And the basis of this is the nucleon-nucleon potential that we developed last time. If you'll recall, if we plot the potential as a function of r for a neutron interacting with a neutron, we found something like this. So as a function of r, we had the potential, and we have some v naught minus area. And so within the value r, you have this attractive potential, and outside that you have nothing. So that might give you a spherical square well potential of a given depth. Recall that for the proton, we modified this slightly, where we had the Coulomb barrier gave part of it, and then we had the potential, and the Coulomb barrier slightly modified the inside as well. So this is for neutrons, neutron. This is for proton, proton. The idea of the Fermi gas model is then, if we add all together the nuclei that we have, they're all interacting each other with a model of this, and we can give a global potential of some kind, which is kind of the average of all these, and we can draw the potential that we expect them to feel. And so if we this will be a spherical potential, but I'm going to draw a cross-section of it for illustration purposes. And so for the neutrons, we expect that there'll be some overall square potential separated by the center, and that for the protons, there'll be a very similar but slightly modified by Coulomb potential going over the same. It'll have the same width, but have these slight edges. And important to note, it will be slightly higher in the middle, this being slightly higher because of the Coulomb potential going there. And so in this square potential, if now you remember the kinds of solutions you expect in a square potential, if we draw them as wave functions, we can draw a wave function that exists here, and there's going to be a ground one which might have one peak in the middle. There's going to be a higher energy potential one which will have a couple nodes, and likewise, and so then we can get more and more potentials going higher and higher in energy in such a fashion, and those levels will be discrete, and each time we go to another higher level, there'll be a given energy spacings, so that in the end, what we might expect, if I get rid of the wave functions and just draw the levels as in the energy. So we might expect levels that look like this with some spacing, and those levels get filled up by the neutrons and protons in their respective shells. And so, however, I also need to keep track of the spins, and as we know that neutrons and protons are fermions, I can fit two protons on a particular energy level as long as their spins are opposite. And so if I start on, and I put protons over here and neutrons over there, I might have a spin up neutron and a spin down neutron in my lowest energy levels, and then I might have a spin up proton and a spin down proton, another spin up proton, a neutron and a spin down neutron. And I can go on filling up these levels up to some energy. And then maybe I'm going to have one last one up here, and that's the last one I added. And that gets filled up to a given level. And in analogy to metals in a in solid state physics, where you have bands, you fill up all the energies up to the Fermi level, Fermi energy, and so that Fermi energy we can label something like this. And so in this diagram, we fill up all the available levels for both neutrons and protons up to the Fermi energy, which is some energy above the depth of the potential, which we can call V naught, down to that bottom of the potential, and then we go up by some energy of the Fermi energy. Now, it has to be the case that the Fermi energy level is the same for the neutrons and protons. Otherwise, you would gain energy by changing one neutron into a proton or one proton into the neutron, so that Fermi energy level is the same for the two. And that's true because we can change a neutron into a proton by beta decay. In this model, we have a gas of neutrons and protons filling up all the levels. It's important to note that that gas is at temperature equals 0, so that we have a Fermi gas of particles, a gas of fermion particles, like electrons in a metal, are also a Fermi gas. And the occupancy level, if we think of it as occupancy level, is 100% out to the Fermi energy, and then it goes to 0. If the temperature rises in Fermi gases, this tends to become changing, and that gives rise to the way real Fermi gases interact. A lot of condensed matter physics deals with that. But in our case, we have T equals 0, so we fill only up to exactly the Fermi energy, filling all these states going up to the top, and then we stop, and we have a sharp cutoff. And so erase that part and keep going. So in the model then, we can then count up all the states that are in this model, and that will tell us something about what we might expect the depth of the well to be and how much the Fermi energy can be. In fact, first we'll do the Fermi energy calculation. And let me start with a clean page. So for the Fermi energy, we imagine that we fill up all the low energy states up to some point. And for every energy level, there's also a momentum. And so we're filling in a volume around the origin of the momentum states around some level. And so to calculate the how big that is, we associate the Fermi energy with the magnitude of a Fermi momentum, which is, we just find classically, p squared over 2m. And then we say we're going to fill up a volume of the space of momentum within that volume. So if we have energies, we fill up all the energies from 0 to the Fermi energy is the same as filling up all the volume of momentum space up to some radius. And we only have smaller momenta than that. And so this volume of momentum space out to PF is just 4/3 pi times that radius cubed, so PF cubed. So that's a volume in momentum space. Now, to do the counting of states, we make use of the Heisenberg uncertainty principle. So Heisenberg uncertainty principle says, okay, we know that we can only measure the position and the momentum in that same direction of a particle to no better than h bar over 2, which means that if we go into a phase space of all the positions and all the momentums, that each state can only occupy a given volume of that state space. And so the volume of this state space then is going to be something like the little volume of momentum space times a little volume of this state of the physical space cubed, right? So, each element of each nucleon can only occupy one of these little chunks of momentum space that's using both the Heisenberg uncertainty principle and the Pauli exclusion principle. And then we can count up the volume of the states space then using the Heisenberg uncertainty principle, and we're just going to use 2 pi h bar cubed. So Heisenberg puts this factor in, and then we cube that, and I see that I've written a square instead of a cubed. And then we're going to add up all this total from all the particles we have, and so we're going to say the V total is a volume of momentum space times the volume in momentum space contained within the Fermi momentum, which we haven't determined yet, times the volume of the actual nucleus, and that volume is the product of those two volumes is the phase space volume, and multiplying those factors, we have 4 pi over 3 rho f cubed, and then the area of the nucleon, this 1.2 Fermi factor, cubed times the number of nucleons that we have, that's the physical volume, and I forgot there's a 4 pi cubed times this this volume as well. So that's a volume for all the nucleons together. And when we solve for that, we can convert this into the number of fermions going out. We also have to remember that there's a factor of 2 for the spins being up or down, but then the number we have up to the Fermi level is just going to be 2 times this V tot times the volume of one of these states that we had before. And when we calculate that all plugging in from above there, we find that this is 4a, the number of nucleons A, over 9 pi times R0 times rho Fermi divided by h bar. All of that cubed. So for a nucleus with n, so if we assume that n equals z equals a over 2, then a over 2 is, and then plugging this in for a over 9 pi R0 rho pf over h bar cubed, we can find that the Fermi momentum is in fact something like h bar over r naught 9 pi over 8, the cube root of that. So notice when we do that, that the momentum is independent of A because the volume grew with A and we then divided out the A. So calculating that factor then, we can find that the Fermi energy, Fermi momentum over 2m, h bar squared to m r naught squared 9 pi over 8 to the 2/3. Recombining some factors, h bar times c squared over 2 mc squared, plugged in a c on top and bottom, r naught 9 pi over 8 to the 2/3. This is 197 over 1.2 squared. This is r naught squared. Times 1 over 2 times 940 MeV for the neutron. And then this 9 pi over 8 factor is just 2.32 once we take the cube root. And that is all 33 MeV. So in this square well, the depth, or from the bottom to the Fermi energy level, is 33 MeV. And it turns out that V naught typically is 40 MeV. And so we can calculate that. Note that this means that the Fermi momentum in energy equivalence, when we calculate out p squared over 2m, is 250 MeV. 250 MeV over c, putting the c back in. That's a pretty big momentum for a particle. And so now note, so since V naught and the Fermi energy are roughly constant, it's actually the physical size of the well that changes. And if you're imagining putting in different levels up to some amount, as you go up, the spacing of those levels, since they always go up to the same point and they have the same level, but there has to be a proportionality between them to fit more in, the spacing of these levels, so spacing here, delta must be proportional to 1 over a. As we put more in the same space, the spacing between the levels has to go down as 1 over a. Okay, so then let's think about the pairing term of the semi-equivalent, semi-empirical mass formula. I'm going to go page for here, and I'm going to draw my standard well. That's the proton part. Here's the neutron part. And I imagine that I've filled up all the protons up to some level and all the neutrons up to some level. And I'm going to draw in the top ones. So imagine that I have a fully filled in set where I have an even number of neutrons and an even number of protons, and I fill up the levels so that at the top level I have a pair of protons. At the top energy level I have a pair of protons and a pair of neutrons. And I start from there. Now imagine what happens if I take one of my neutrons and what I want to do is I want to erase it from here, and I convert it into a proton. It has to go to a higher level because there was no lower level to go to. And you see when I do that, one neutron goes to a proton. I take the neutron and I raise it to a higher level. I get +1 delta for how much energy it takes. Okay, and so then I do that again. So I erase this neutron, if I can. There we go. And I put it up here. Again, I've raised by 1 delta. So that's 2 total, because I still have the other one. Now, I want to do it one more time, and so I need to have, remember that I have lower ones here. So these are the next level down. The third one that I move, then, I erase one of these, and I put it up here. But notice, I erased one lower than I had for the first two, right? One lower, because I started here and I went one down, and I had to go one higher. So my third one changes by 3 delta. Likewise, the fourth one is going to change by 3 delta. But the fifth one, I'm going to hollow out one more neutron, and you have to go one higher in the proton. And so then I'm going to be changing by 5 delta. And notice for these odd ones, the first one gets changed by 1, the third one gets changed by 3, the fifth one gets changed by 5. That's saying that every time I change, the more I change, the more I have to change at the same rate. And so that means that I should definitely expect then there to be an energy cost for that of n minus z squared. Right, so here's, I've changed n minus, so between these I changed n minus z by 1 in each case, and I had one change. Here I changed by 3, but I had a 3 change, so that's 1 n minus z from the change, and an extra factor of that from how much I had to change with that. So that's why I have the n minus z squared factor, or as it is, you can also sometimes see it as z minus a over 2. In this case, you would have the same, about the same thing, but the factors may be different. But also the delta changes with a, so in the end there's a factor of a dividing this. And that explains the pairing term of the semi-empirical mass formula, why it has the form it does.